All right, today we're going to dig into something that sounds, well, a little weird. Multiplying two arrows together. But trust me, hidden inside that simple idea is a secret. It's this powerful language that can describe everything from pushing a box across the floor to the actual shape of the molecules that make up our world. So let's go find that secret.
So let's just start with the big question right up front. I mean, we all get how to add and subtract vectors. You know, those arrows that have both a direction and a length? But what does it even mean to multiply them? It sounds kind of strange, right? Well, there's a special way to do it, and it's called the dot product.
Now, if you just look at the math, the calculation itself seems almost too easy. You literally just multiply the matching parts of your two vectors, u and v, and then you add all those little results up. That's it. It's a super straightforward process, and it spits out a single number. But the real question is, what is that number?
Let's just run through a quick one. Say vector u is 3, 0, 1, and vector v is -2, 1, 4. We just go piece by piece. So 3 times -2, that gives us -6. Then 0 times 1 is, well, 0. And finally, 1 times 4 is 4. Now just add them up. -6 plus 0 plus 4 equals -2.
And this is where the mystery really starts. We took two vectors, two arrows pointing somewhere in space, and we didn't get another arrow back. We got a single number, a scalar. In our case, it was -2. But what is that number? What is it trying to tell us? Because this isn't just some random result, it's a clue.
Okay, here's our very first clue. If the angle between two vectors is acute, so less than 90 degrees, their dot product will always be a positive number. That tells us they're pointing in generally the same direction.
Clue number 2 is honestly even more powerful. If two vectors are perfectly perpendicular, sitting at a perfect 90-degree angle to each other, their dot product is exactly 0. No exceptions. This gives us an incredibly easy test for what mathematicians call orthogonality.
And our final clue for now. If the angle between them is obtuse, so more than 90 degrees, the dot product will be negative. This means our vectors are pointing in generally opposite directions.
So let's just pause and think about that. The sign of our mystery number, whether it's positive, 0, or negative, it isn't random at all. It's packed with geometric information. It's basically a quick report on how our two vectors are oriented relative to each other. But can we do better than just acute or obtuse?
Oh, absolutely. To get the exact angle, we can do something really clever. We arrange our vectors, u and v, so they start at the same point. Then, if we draw a third vector that connects their tips, we get a triangle. And this is the key, because the geometry of that triangle holds the secret, and we can unlock it with a powerful tool called the law of cosines. And when you actually apply the law of cosines to that vector triangle, something amazing happens. It's like we just found a Rosetta Stone, you know, the key that lets us translate the simple algebra of our dot product into the rich visual language of geometry.
And this is it. This is the secret. The dot product of u and v is also equal to the length of u multiplied by the length of v multiplied by the cosine of the angle between them. So that simple little calculation we did, it's not just a number. It's a profound statement about the vector's lengths and the precise angle that separates them.
This formula is the bridge, the connection between the algebra and the geometry. And now that we have it, we can unlock some truly incredible things. Let's see what this baby can do. First off, remember our test for perpendicular vectors? Well, now we know why it works. The cosine of 90 degrees is 0. So if the angle is 90, that whole right side of the formula just becomes 0. So, you want to know if two vectors form a right angle? You don't need a protractor. You just find their dot product. If it's 0, they are. It is just that elegant.
But this is way more than just a math trick. Let's talk about the real world for a second. In physics, the idea of work is how we measure energy transfer when a force moves something. And it turns out the dot product is the perfect, natural language for this idea.
Think about it. If you're pushing a heavy box, but you're pushing down on it at an angle, only the part of your force that's actually pointing in the direction the box is moving is doing any useful work. And that cos theta term in our formula, it perfectly isolates that exact component. So work is quite literally the dot product of the force vector and the displacement vector.
Here's another beautiful use for it, finding a vector's projection. Just imagine shining a flashlight from directly above vector v. The shadow that vector u casts onto v, that's its projection. It's basically a way of asking, hey, how much of vector u is pointing in the exact same direction as vector v?
And take a look at the formula we used to calculate that shadow vector. Bam! Right at its heart, there's the dot product, u dot v. That's the part that determines how long the shadow is. And this idea is absolutely fundamental in things like computer graphics for realistic lighting, or in engineering when you're breaking down complex forces.
So we've seen it in geometry, we've seen it in physics. That's all cool. But can a simple calculation like this really describe the fundamental structure of matter itself?
Well, let's take a look at the humble methane molecule, CH4. You've got one carbon atom in the middle and 4 hydrogen atoms that all try to get as far away from each other as possible. When they do that, they form this perfect geometric shape called a tetrahedron. So what's the angle between those chemical bonds?
We can figure this out with the dot product. We can just decide to place the carbon atom at the center of our universe, at coordinates 0, 0, 0. Then we can place 2 of the hydrogen atoms at positions that we know will form that tetrahedron shape. And just like that, we have 2 vectors, each one pointing from the carbon out to a hydrogen.
Now we just use our formula, we take the dot product of those 2 vectors, we find their lengths, and we solve for the angle. And the result? 109.5 degrees. Now that is not just some answer to a math problem. That is the actual, experimentally verified bond angle in a real methane molecule. It's a constant of nature, and we found it with this simple tool.
We started with this simple, kind of weird calculation, just multiplying and adding some numbers, and we ended up revealing a fundamental constant of chemistry. It just makes you wonder, right? What other profound secrets about how our universe works are just sitting there, hidden inside simple mathematics, just waiting for us to find them?